Hi, I'm Bob Stern.
Hi, I'm Yasuhara.
Good afternoon. My name is Fernando Martinez.
I'm Jian Lin.
A lot of interesting science has resulted from studying the 2,800 kilometer long Izu-Bonin-Mariana convergent margin. In this presentation, we'd like to address some of the deep scientific challenges that can be addressed in the southernmost Marianas. This region attracts global attention because the Challenger Deep, the deepest point in the ocean, is here. Within the past decade, two men wealthy enough to build their own deep diving submarines have dived to the bottom of the Challenger Deep. In both cases, they landed on some of the least interesting real estate in the region, a flat seafloor blanketed in pelagic snow. This pelagic snow is composed mostly of fragments of a large diatom, Ethmodiscus rex. Other parts of the region are much more tectonically active, as shown by a 7-month deployment of ocean bottom seismometers. Zhu et al. In 2019 recorded more than 7,000 earthquakes within a 300-kilometer radius of the Challenger Deep, an average of more than 30 earthquakes per day. The southernmost Mariana region is interesting because it is so different from the rest of the Izu-Bonin-Mariana convergent margin. There are three main differences. First, the forearc as measured by the arc trench gap is much narrower. Second, big stratovolcanoes are missing. And third, the back arc basin spreading axis is much closer to the trench. All three differences are related to the youthfulness of this convergent margin and the importance of trench parallel extension. We know from GPS studies that the southernmost Mariana convergent margin is deforming very rapidly. We can only use GPS to measure relative motion where there are islands, and so cannot use GPS to measure movement south of Guam. Nevertheless, a clear pattern of extension rates increasing from near zero north of 20 degrees north to 45 millimeters per year at the latitude of Guam has been determined. Extension rates south of Guam are likely to be higher than 45 millimeters per year. As a result of strong extension, the southern Mariana convergent margin shows a strong volcano-tectonic fabric. Extension is complicated in the region, with a strong component of north-south extension as well, as shown by left lateral earthquake focal mechanisms along the West Santa Rosa Bank Fault. This fault is the sharp eastern boundary of the southernmost Mariana extensional realm, and these focal mechanisms indicate that north-south extension is also important in the region to the west. The Malaguana-Gadao spreading ridge is the southern continuation of the back arc basin spreading ridge. This spreading axis bends west and ends in the east-central part of the basin. This diffuse spreading zone is the western continuation of the back arc basin spreading ridge, but extension is not focused at a well-defined plate boundary here. The southwest Mariana Rift in the far west reveals a more focused extensional style, and today is very tectonically active, as shown by concentrated seismicity in this region. Extension has strongly affected the magmatic arc. Lithospheric stretching above the deeper source of arc magmas has formed the Finanagu volcanic complex and the Alphabet volcanic province. The strong extension in this region distributes the arc magmatic flux, preventing growth of large stratovolcanoes. Instead, arc magmatism is spread out in the direction of extension, as seen for the Finanagu volcanic complex. Here, extension seems to have been oriented northeast-southwest. Finally, a broad zone of magmatic extension that occurred 2.7 to 3.7 million years ago formed the southeast Mariana Forearc Rift. Regions with volcanic activity so close to the trench like this are very unusual in forearcs. Another interesting feature is what appears to be a field of several dozen small volcanoes just north and west of the West Mariana Ridge, between 12 and 13.5 degrees north. These small volcanoes are scattered over a region that is about 300 kilometers long and 200 kilometers wide. The composition, age, and tectonic significance of these volcanoes is unknown. Some energetic young scientists should start investigating these volcanoes. The strong volcanotectonic fabric of the southern Marianas margin strikes at a high angle to the trench, indicating that it formed as a result of trench parallel rifting of the older margin and volcanic accretion of new seafloor. There is also a lot we don't understand about the role of the Oligocene-Caroline plate and how this affected the southern Mariana Yap convergent margin. Extension of the southern Mariana margin changed the orientation of the margin from more orthogonal to more oblique with respect to the west-northwest directed Pacific-Philippine relative velocity. As the forearc widened, new regions of the Pacific plate began subducting underneath it. The youthfulness of this subduction zone is shown by the shortness of the subducted slab beneath the southernmost Mariana convergent margin. The maximum depth of the subducted slab here is everywhere less than 250 kilometers, much shorter than the approximately 670 kilometer depth of the subducted Pacific plate farther north. The maximum depth of the subducted slab beneath the southernmost Mariana convergent margin decreases from about 250 kilometers in the east to 100 kilometers in the west. Assuming that present convergence rate with the Pacific, about 30 millimeters per year, simple math suggests that subduction began about 8 million years ago in the east and 3 million years ago in the west. The interaction of multiple tectonic elements, collision, shearing, subduction of Pacific Caroline lithosphere, and back arc basin extension resulted in the complex volcanotectonic fabric of the southern Mariana convergent margin observed today. Over the past 5 million years or so, the combined results of collision, back arc extension, shearing, and subduction initiation resulted in the complex fabric we see today. Forearc crust for most of the Izu-Bonin-Mariana convergent margin formed during subduction initiation in Eocene time, but southern Mariana forearc crust formed differently. Widening of the southern Mariana convergent margin must be mostly accomplished by basaltic volcanism, and the best evidence for this is in the southeast Mariana forearc rift. There is evidence for basaltic volcanism farther to the west along the forearc, but this region is poorly explored. Mechanical extension must also have played an important role because samples from some blocks are 46 million years old. We're only beginning to understand what the southern Mariana forearc is composed of, especially the distribution of older rocks and younger basalts. To a first approximation, it is likely that regions shallower than 3 kilometers below sea level are mostly composed of older crust, and deeper regions are mostly underlain by young basalt. All of the extension and magmatic activity in the southernmost Marianas has set up conditions for hydrothermal vents. We know about 6 active hydrothermal vents in the region, and we've also discovered a fossil chimney. There are likely many more hot, strong hydrothermal vents waiting to be discovered in the region because we have only looked for these along the spreading axis and isolated volcanoes to the east. Almost nothing west of 143 degrees east has been surveyed with the proper tools. There is also at least one cold seep along the inner trench wall, marking where fluids that have interacted with mantle peridotite and are rich in methane vent to the ocean. This is the Shinkai Seep Field, which we stumbled on in 2010 while studying the petrology of the inner trench wall. Methane from these vents builds white brucite chimneys and supports vigorous biological communities, including clams, snails, and brittle stars. We have much to learn about the crustal structure of the southernmost Mariana convergent margin. A recent geophysical experiment across the southwest Mariana Forearc Rift shows that the crust beneath this region is 12 to 18 kilometers thick. Shinkai 6500 diving on the inner trench wall near the Shinkai Seep revealed the crust mantle boundary lies about 5,800 meters deep, indicating a crustal thickness here of only 2 kilometers. There's almost 5 vertical kilometers of mantle peridotite exposed below the moho here, providing unparalleled opportunities to study the mantle in situ. We haven't begun to study the subducting Pacific plate in this region, and we need to. We don't even know the age of the crust being subducted. 6 holes were drilled in the region by the Deep Sea Drilling Project 50 years ago, but give ambiguous results for the age of the seafloor subducted beneath the southernmost Marianas. DSDP drilling reveals that crust about 300 kilometers to the south is dominated by Oligocene rocks, much younger than the Mesozoic crust drilled 500 kilometers to the east. Swath mapping reveals major normal faults on the outer trench slope that formed as the Pacific plate bends into the subduction zone. The bending of the Pacific plate here is unusually sharp, with a much smaller radius of curvature than is seen for the plate farther north. It is unclear why the Pacific plate is so sharply bent. The subducted slab may be young and weak, or outflow of a cenosphere from the Philippine Sea may be responsible, but the bending of the Pacific plate here must be accomplished by normal faults that are unusually closely spaced or have unusually large displacements, or both. These faults may allow seawater to infiltrate deep into the lithosphere, expediting serpentinization of the downgoing plate, further weakening it, and allowing it to bend more sharply. In order to address these questions, we need to begin exploring the Pacific plate adjacent to the southernmost Mariana convergent margin. A wide range of studies are called for, but above all, we need to constrain the age of the lithosphere. This question can best be answered by drilling. We hope you enjoyed this brief summary of what we have learned and wonder about the unusual convergent margin around the Challenger Deep.